Hi, and welcome to Acoustics in Architecture webinar by Knauf Insulation. Why did we decide to dedicate a webinar to acoustics and architecture? It's architecture and the architects who today have the central part of the design process. The architects are imagining the spaces, shaping the spaces, and ultimately bringing these spaces to life. And today, more and more, the design is done around the concepts of well-being and comfort. And one very particular and very important aspect of the comfort is acoustics. And that's why we want to talk to you about the importance of acoustics and to present you tools, materials, and design techniques you can use in your own daily work to create acoustically beautiful spaces. My name is Maro Pulzejevič, and I'm an acoustician in the Research and Development Department of Knauf Insulation. During my career, before dedicating myself to research activities, I was fortunate to work as the acoustic consultant on some of the large international projects, which are designed by some of the biggest names in the world of architecture, such as the recently inaugurated Al Janoub Stadium, designed by late Zaha Hadid, which will be used for the upcoming 2022 Football World Cup in Qatar, or another project in the Middle East, this time a 230 meters tall tower designed by the French superstar architect Jean Nouvel, or this beautiful Mondrian Hotel designed by the famous Dutch architect and designer Marcel Wonders. So the key messages this webinar shall address are: why is acoustics important in the first place? And in this introductory part, we shall discuss the fundamental benefits of acoustics. How to add value with acoustics. Here, we'll capture the essence of the architectural work and look into acoustics not as a strictly technical discipline, but more as a tool which can be used to add value both artistic and economic to the project. Of course, as the core business of us at Knauf Insulation is manufacturing mineral wool products, we shall address the role of mineral wool from the acoustics point of view, and we shall discuss the properties which are responsible for exceptional acoustic performance that mineral wool delivers. Central part of the webinar will focus on the fundamentals of acoustic design and actual strategies which are utilized during the acoustic design process, and which will enable you to address any acoustic challenge you might face on your future projects. We shall also talk about the particular solutions that Knauf Insulation has in its portfolio for each particular application, and ultimately, we shall take a look into some common problems and challenges that inevitably arise during the course of the project. Why acoustics in the first place? And let's for a moment shift our attention from that first and the most obvious answer which immediately comes to our minds, which is to comply with acoustic regulations. So let's go deeper than that, and let's discover the true benefits of this beautiful but sometimes mystique engineering discipline called acoustics. So what can be more important to us, to human beings, than the health? Our well-being and comfort have been, in one way or another, the focal point of the architectural design, as well as one of the strongest real estate selling points for a long time. The World Health Organization says that noise can disturb our sleep and seriously harm human health. It can also reduce performance and provoke changes in social behavior. And I'm pretty sure that all of us can relatively easily agree with these words and identify ourselves with these statements. I'm certain that, well, more than once in our life, we did not sleep quite well because of the loud neighbors, because of the loud traffic noise, and most likely we did not feel so good the next day. We were maybe in a bad mood, or bitter with people around us, or just less productive at work. According to the statistical data, 50% of Europe's population is actually burdened by noise. In France, scientists actually went so far and tried to put a figure to the expenses provoked by various health-related problems, all triggered by noise. And they came to this astonishing figure of 11.5 billion euros per year, which are lost due to the employees being unable to go to work because of sleep deprivation or cardiovascular problems. all related to excessive noise and to poor acoustic conditions. And when unfortunate situations like these happen, the first place where we all go are of course the hospitals. So hospitals are very particular buildings which are expected to improve our health. And that same health which might actually be worsened by noise. And now we can easily find ourselves caught with a very difficult problem that noise-related issues are expected to be solved in institutions such as hospitals, which themselves could easily have problems with poor acoustics. And that is actually quite a common situation in hospital buildings worldwide. And here's a strong statement from UK Department of Health on how important the good acoustic design in hospital is. A good acoustic conditions improve patient privacy, dignity, and promote essential sleep patterns. Such conditions are key to healing. Let us look into another extremely important aspect of our lives and another particular building type whose quality is very closely related to acoustics. That's schools or our education facilities. One of the working groups of American National Standards Institute finds that percentage of speech intelligibility in schools is 75% or less. So what does that actually mean? Well, let's imagine that you are reading a book and every fourth word from this book is erased. Now you're expected to actually understand the content of such a book and eventually take the exam on the subject. So I think we can all agree that would be quite a difficult task for any student. And that's the actual situation in our schools. So our children, besides many other challenges imposed on them, are challenged just to understand and properly hear the subject. And this particular problem is emphasized even more in our modern day society, in the world which is becoming smaller and smaller and more international. So let us now imagine the situation in a university where a non-native speaker, such, let's say, a professor which comes from France, is teaching a class in university in London and his students are predominantly Chinese. So if we pair all these components with the poor acoustic conditions of a lecture hall, I would say that qualifies as quite a challenging task for both parties, students and the professor. And what about offices? Apart from our homes, offices are the spaces where we spend the majority of our time. And actually, our modern offices did not change too much from these early open office experiments back in the days of Taylorism. And it's interesting to read the conclusion of one of the latest studies done by Cornell University, which says that noise is the most common source of complaints in the offices. And again, I'm confident we can all identify ourselves with that. Whether we work in an open plan office and we are disturbed by the conversation of our colleagues, by phone ringing, shredding machine, or just a coffee machine. Or we work in an individual office and we lack sufficient privacy from surrounding spaces. Of course, at the end of the day, all these distractions have a significant impact to our well-being and to our health. But it's also interesting to consider the aspect of the loss of productivity and eventually the impact that has to the profitability of the company itself. And it's exactly the profitability and this interesting relationship between the economic benefits and acoustics which has been in the focus of the recent scientific research. According to the results of various studies, there is an actual relationship which indicates better sales records with better acoustic environment, either in retail spaces, restaurants, even in hotels as a part of a customer retention program. And there is an interesting information that retail sales at the Glasgow airport increased by 3 to 10% thanks to the improved acoustic environment. And as you can see, we're now slowly moving away from the health benefit of acoustics and we are entering into the area of profitability and the added value, which is a very interesting subject these days, particularly from the investor's point of view. So therefore, we come to a very legitimate question: how can we use acoustics to increase the property value? The earlier example illustrated well how this works in the retail space. But can we come to a similar conclusion for a classical residential or housing projects? Yes, intuitively we can say that apartment which provides better sound insulation from outside noise or from the noisy neighbors deserves to be sold at a higher price compared to the apartment which has poor sound insulation. However, in real life, such a feature is not so easy to recognize when you are just a typical buyer of the apartment. Well, even if you are an engineer, an experienced engineer, it would be quite difficult to estimate the acoustic quality of a wall just by knocking on it. We might understand, is it a dry wall, is it a block wall, but unless we go on the other side and we play some music or increase the volume on TV, we will actually have a difficult time to define the acoustic quality of an apartment. In the world of thermal insulation, this particular challenge has been overcome by introducing energy certificates. And these energy certificates became mandatory document while buying, selling, or even when renting the apartment. And exactly along the lines of the energy certification, the acoustic classes are starting to find their way into the acoustic regulations. Some of European countries have already introduced acoustic classes. For the moment, these classes are not yet mandatory, but they do provide a good indicator of the acoustic comfort you get for your money. With a tool like this, it will very quickly become a reality to be able to pay extra for a luxurious level of acoustic comfort, which can provide better sound insulation compared to the regulated baseline. So therefore, it's very soon that we will see a straightforward relationship between the acoustics and the value of the property. So on the same lines as we are ready to pay more for a good thermal insulation, which will eventually reduce the cost we pay for electricity or a gas on a monthly basis, we will be able to pay more for the comfort and for silence, as well as paying less for a property which does not deserve to be classified as luxurious only because of its nice interior decor or a classy furniture. So those were some principal benefits of acoustics. We mentioned health, we mentioned comfort, productivity, profitability, and the increase in the property value. But besides these, there is another very important aspect of acoustics, which is maybe even a fundamental one for you, for the architects. And that aspect is how to complement our design with acoustics. Some similar concepts, which are maybe more evident, are the importance of colors or the importance of light in the design. So these days, everyone is aware that we can easily make a room look higher or larger with the correct selection of colors. So the good question is, how can we achieve such effects with acoustics, and how can we utilize acoustics as a tool to amplify the message that we want to send with our design? So this is a magnificent hall of mirrors, which is the most famous room in Versailles. Architecturally, aesthetically, from the first glance, it is evident this space is sending the message of glamour, the message of power, of luxury. But let's now do an effort. Let us together try to imagine how does this space sound. So for the moment, let's travel back in time and let's imagine the king, Louis XIV, for example, entering this space and with all his entourage waiting for his appearance. So thanks to the extensive use of stone and glass in this space, in the acoustics vocabulary, we would say this space sounds reverberant. So that means that every step that the king takes, and please, let's not forget that men were wearing high heels in that period, so every step resonates throughout the space and king's presence is powerfully felt in the entire hall. So this is just one example how we can use acoustics to accentuate certain messages we wanted to send with the standard frontline design features, which are usually the interior design or the selection of materials. And now, let's again travel in time to a present-day France. And let's keep the similar architectural, even the acoustic setting. So this is the Blue Train restaurant in Paris, as French would say, Le Train Bleu, and it's located in one of the busiest train stations in the world, La Gare de Lyon. So if you now wonder how this space sounds, I find one of the reviews from the TripAdvisor very illustrative. It says huge, noisy, busy, but atmospheric. So for a luxurious restaurant, a designer would typically target the private setting, the quiet environment where people can have an undisturbed conversation and generally relax without overhearing the conversation of others. However, the architectural and design team behind this restaurant wanted intentionally quite the opposite. And they used acoustics to achieve that. So again, they used a lot of reflective surfaces, they created the reverberant space, and by doing so, they managed to extend the busy atmosphere of the train station inside the interior of the restaurant. And the result is this noisy and busy atmosphere. Well, maybe this is not a restaurant for everyone, and surely it's not the restaurant for every possible occasion. But one thing is sure, is that you have to book well in advance to get the seat in this restaurant. And just as a quick comparison, here is another restaurant which inspires completely different acoustic environment. So just by using more softer materials like curtains or leather, it's easy to create, well, both visually but also acoustically, more private atmosphere, quieter and intimate settings. So you see, as architects, once we start to include our ears and acoustics in the design process, a whole new dimension of opportunities opens up. And the possibilities with acoustics for you as architects are endless. We have mentioned the word noise quite a few times so far. So what is actually noise? The usual definition of noise is that the noise is an unwanted sound. And we can agree that that is quite a subjective definition. So how do we actually define what is unwanted? Generally, this depends on two things. First one is the level of sound. So the level of sound is expressed in decibels. And here is a very simple illustration of different magnitudes for the level of sound. Let's look at the bottom of our thermometer, and 30 dB, which corresponds to a very faint sound or a whisper. A normal level of human conversation will range between 40 and 60 decibels. Typical traffic noise in a typical urban area amounts to 65 to 70 decibels. And extreme levels of 90 or even 100 decibels, which can already cause pain or serious damage to our ears if we're exposed to them for a long period of time. And these levels would correspond to a loud music we experience at rock concerts or to a noise of a jackhammer. So on the other side of what defines the noise is a frequency. And frequency is measured in hertz. A range of frequencies that humans hear ranges between 20 and 20,000 hertz. So very low frequencies, let's say below 100 hertz, correspond to something that we usually associate with the bass level. So that would be the beats in the electronic music. Then frequency between 100 and 500 hertz would closely correspond to the hum of the traffic. So generally, we can still refer to this range up to 500 hertz as the medium to low frequency range. As we go higher to around 500 to 1000 hertz, those are the frequencies which are predominant in the human voice. And as we go even higher, we reach very high frequencies, which are something that we understand when opera singers are trying to hit those high notes. So it's this very fine relation between the level and the frequency which will cause our brain to define which sound is pleasant and which sound is unpleasant and eventually unwanted. But for instance, the bird song at 60 decibels might be less annoying than the clock ticking at 35 decibels. Or we might find the waterfall noise at 80 decibels quite pleasant, but on the other side the traffic noise at 60 decibels can already drive us crazy. So it's not always that the loudest sound is the most annoying one. Frequency will also play a big part in reaching this very subjective judgment of calling something noisy. And let's see what happens in the real life when noise takes over and things on our projects get out of control. One of such notorious acoustic examples is the Business Academy, Bexley, which is located on the outskirts of London. And it's very interesting that this project was shortlisted for the Sterling Prize by the Royal Institute of British Architects. And it was designed by one of the top architectural firms in the world. This is the outside appearance of the building. So I'm not an expert on aesthetics, but we might agree that the building looks quite nice to an average observer. This is the inside of the building, and this is where interesting things for us acoustically start to happen. So in order to foster the open space approach and collaboration, communication between the spaces, classrooms were designed without the back walls. You can notice that on the image. And by doing so, by removing the back walls, the classrooms were connected to this large interior atrium. So what actually happened on the very first day of the school? The noise between the classrooms resonated so much through the atrium that students were not able to hear the lecture. And the outcome? The school had to be closed, and the local authority had to invest $850,000 on noise mitigating solutions. And these noise mitigating solutions were actually these panes of glass that were installed at the classroom's back walls. So today the classroom and the school looks like this. So all the classrooms are being enclosed, and that original idea of having open and connected spaces was actually abandoned. So this is a very good example how an idea which might sound really good at the early stages of the project can easily turn to be a very problematic from an acoustics point of view. And in the end, to summarize this introductory part of the webinar, we have mentioned a variety of positive aspects of the acoustics which go beyond the compliance with acoustic regulations. And these include health aspects, comfort, functionality of the space, impact to productivity, as well as the increase in profitability. We also saw that acoustic design can be used as a powerful tool to increase the value of the property, and as the design feature which we can incorporate within the fabric of the architectural design. And as a final thought, the good acoustic design is important everywhere. It's not only a privilege of opera halls, but it's also a very important aspect of residential buildings, schools, or even restaurants. Now that we know that acoustics is important, let us take a look at the product that we at Knauf Insulation are manufacturing, at the mineral wool. So this part of the webinar shall address the role of the mineral wool from the acoustics perspective. So we shall talk about the particular characteristics of mineral wool which make it such an interesting product for the acoustic applications. And this is how a typical piece of mineral wool looks like. I think we've all seen it, we've even touched it before, and yes, you could say it doesn't look so spectacular. However, let's take a closer look with the microscope, and we might find that our perspective will change. So here's how the mineral wool looks under the microscope. To give you an idea of the scale, so diameter of these fibers is around 5 to 10 micrometers. So with this image in mind, we already can intuitively start to understand that the sound will have quite a difficult task to pass through this network of pores. So while the sound is doing its best to move through this dense network of pores, a certain physical phenomenon happens. We call this physical phenomenon the loss of acoustic energy. And this loss of acoustic energy is governed by many parameters. But we can say that the most important ones are the fiber orientation, fiber size, the density of the entire insulation package, and of course the chemical composition. So something that we agreed didn't look so spectacular at the first glance is actually a very sophisticated product with a lot of room for the optimization of its performance. You can easily imagine that acoustic properties will change if our fibers are more thicker or thinner, or if the fibers are parallel or perpendicular to the sound. So these are all the parameters that our experts, our scientists and acousticians in Knauf Insulation investigate with a great attention. So we do our best to optimize these parameters into a final insulation package that will be suited for a particular application. And I'd say that this is one of the key strengths of us at Knauf Insulation. Our knowledge, our experience and our expertise, and the amount of efforts that we invest into the research and development of mineral wool. From the raw material, through the production line, to the final product which is packed and eventually delivered to you to the construction site. When mineral wool materials are discussed, there is usually a strong debate around which material is the best. Is that the wooden wool? Is that glass mineral wool? Rock mineral wool? So what I always like to point out and emphasize is that each of these materials has its own strong points. So it's up to the particular application to define which material will be the best. And that's again one of the strong points for us at Knauf Insulation, because we are manufacturing all these mineral wool products: blowing wool, wood wool, rock mineral wool, and glass mineral wool. So we are able to recommend a product which actually suits a certain application the best. So what actually happens with the sound when it hits the surface of the mineral wool? So part of the incoming sound is reflected back to the space where it originally came from. The part of the sound is absorbed within the material, within that complex network of pores that we saw, and the part which finds its way through the structure, on the other side, we call the transmitted sound. So these are the three main components which govern the acoustic performance of materials. The ratios and the magnitudes of reflected, absorbed, and transmitted sound determine the material's acoustic properties, and basically the possible use of a certain material for acoustic purposes. Because of the porous structure of the mineral wool, we say that the principal parameter of mineral wool's acoustic performance is sound absorption. So what is actually sound absorption? There are a lot of mind-twisting definitions for sound absorption. There are a lot of theoretical expressions to define the sound absorption, but I find a very convenient way to describe this property by looking at two opposite acoustical properties, which are the sound reflection and the sound absorption. So very intuitively, without any deep theoretical knowledge, we can very easily differentiate between materials which are more acoustically reflective and which are more acoustically absorptive. While glass or stone will be more reflective, fabric for the curtains or leather, as well as mineral wool, will be more absorptive. So sound absorption, which sounded very complicated in the beginning, is nothing more than the way to express this characteristic of a material to reflect the sound back to the space or to prevent its reflection. And this ratio of reflected and absorbed sound is what we actually measure, and the quantity which we use for that purpose is called sound absorption coefficient. And we indicate the sound absorption coefficient with the symbol alpha. So as with every coefficient, this alpha can range only between 0 and 1. So for very reflective materials, we will have a sound absorption coefficient of 0, or a maximum value of 1 for very sound absorptive materials. And typically, we like to say that the higher alpha value means the better acoustic performance. That is true, but we also saw that there are fine limits to what optimum acoustic performance means for different types of spaces. So yes, the higher alpha indeed means the better acoustic performance, but the optimum value which is required will depend on the reasons behind the acoustic design. Now we can take a look at some actual building materials and understand how to interpret a typical sound absorption chart. And I've put here a small reminder, as we said that the higher sound absorption is generally considered better. And these are the results of standard sound absorption tests for these three materials: concrete, glass, and wood. And before we go into the details of this chart, we do see that the values are rather low and closer to 0 than to 1. So this is immediately indicative that this group of materials has low sound absorption. On the left side of the chart is the sound absorption coefficient, and it ranges from 0 to 1. On the horizontal axis is the frequency range, so don't worry, this is nothing complicated, although it usually looks very confusing at the first sight. So to make things easier for everyone, we have developed a system to express the acoustic performance of materials as a single number. That's very convenient, that makes our lives and coordination on the projects much easier. However, sound is the phenomenon which occurs on a wide range of frequencies, and that's the reason why all the acoustic tests are done on a large frequency range. And in our example, we can notice relatively low sound absorption across the entire frequency range. And now, if we would average these values and we use the single number convention, we could say that these three materials, concrete, glass, and wood, have sound absorption coefficient or alpha of around 0.1. Let's now add some materials to our chart. Some materials which we usually consider soft or acoustically absorptive. These are leather-covered seats, carpet and heavy velour drapes. So as now we can easily read the chart, we can notice that these materials provide much higher sound absorption, and by utilizing single number convention, we can say that these materials have a sound absorption coefficient alpha between 0.4 and 0.6. So you can already imagine a very simple example of an empty room which sounds very echoic, very reverberant. But as we start to add furniture, carpet and curtains, our room becomes less and less echoic. So in a certain way, this is a real-life representation of this chart. Now, instead of these common materials which are used for interior decoration, let us look at some proper building materials such as aerated concrete, EPS, cork or a PU foam. So trends of sound absorption of these materials are very similar to materials from before. And again, we talk about the range of sound absorption between 0.3 and 0.6. So now to make things very, very complicated, I'm going to add all these graphs to the same chart. And in the last step, I will add the sound absorption curve for a standard mineral wool having a medium density. So thanks to the open pore structure, it's evident that mineral wool has a superior sound absorptive performance if we compare it to these other materials, because these materials have more closed structure of the pores. And now we are reaching an alpha value, a value of sound absorption of around 0.9 to 1. And later on, we shall see how to utilize this superior sound absorption in the acoustic design and to solve some actual acoustic challenges. So just a note, all of these charts correspond to materials of similar thickness, of around 30 to 50 millimeters. So the comparison of sound absorption between these materials makes sense in the first place. And here are the messages of this part of the webinar related to the role of the mineral wool. Earlier, we saw the microstructure of the mineral wool and the dense network of pores, which is actually responsible for the acoustic performance. Furthermore, we mentioned several types of the mineral wool: the rock mineral wool, glass mineral wool, wood wool and the blowing wool. And we said that there is no best product or the best technology for all the purposes. The best product and the best technology will be determined by the specific requirement or specific application that is of our interest. And we at Knauf Insulation are manufacturing all these types of insulation. And finally, we saw the excellent sound absorption properties that mineral wool has and the advantage of an open cell structure compared to the closed cell structure. And in the end, we can say that mineral wool as a material has a very important role in the acoustic design, both as a standalone material as well as within building elements or systems, as we are going to see in the next part of the webinar. And here we are. After this initial, let's call it introductory part of the webinar, we are coming to the central part where we are going to talk about the fundamentals of acoustic design and the strategies on how to include acoustics in the architectural design. There are 5 fundamental aspects of acoustic design. So for every single project in the world, no matter of its type, of the size or location, there are these 5 aspects that we have to consider in order to address the entire acoustic design of a certain project. And we can use this image of a very simple object to illustrate all the 5 aspects. The first fundamental aspect of acoustic design is maybe the one that everyone is the most familiar with. That is the sound insulation between the interior spaces of the building itself. Second one is the room acoustics, which refers to the quality of the sound within the space. So that would be something along the lines of the acoustic ambient in the restaurant examples we have discussed before. Third one is the insulation from outdoor noise. So basically the design of the building envelope to provide sufficient insulation from the outdoor noise. Next one, the noise of building services which are heard inside the building. Those are typically air conditioning systems, ventilation systems, plumbing, elevators, and various items of equipment which are essential for the operation of the building. And the last one is the impact from our building towards the environment. So this aspect deals with the acoustic treatment of equipment which is installed within our buildings or typically on the roofs of our building. So no matter how complicated the project might seem, the acoustic design and the acoustic challenges can be always broken down to these 5 fundamental aspects. So let us start with the first fundamental aspect of the acoustic design, the one that is maybe the closest to everyone, that people usually have in mind when we talk about acoustics. That is the interior sound insulation. At the beginning, it's very important to define 2 principal mechanisms of sound propagation. One is the airborne sound, and the other one is the impact sound. The airborne sound is the sound which travels through the air. So that would be the sound that we hear when someone is singing or listening to the television. On the other hand, there is the impact sound which travels through the structure. And that would be the sound that we hear when someone is walking on the floor above us. So when we talk about the airborne sound and the ways to protect ourselves from the airborne sound, to isolate ourselves from the airborne sound, we use this term airborne sound insulation, and we denoted it with RW. And we say that the higher this RW is, the better it is. And to give you an idea what this means, we shall illustrate the subjective impression of privacy for some basic constructions. So now let's imagine that the person on one side of the wall is talking and we are listening on the other side of this wall. And the wall between us has a certain RW rating, so it has a certain airborne sound insulation rating. If this wall has an RW rating of 30 decibels, which would correspond to a typical glass wall, we would be able to clearly understand the speech, even if this speech was at a normal voice level. Now, if we change this wall and we build a better one, which has the RW of around 40 dBs, which corresponds to a basic dry wall without the mineral wool inside. Now, we can still hear the same conversation, but we would struggle to understand it this time. So this level of insulation is usually considered as the basic for the office space. Now, if we move even further, we upgrade our wall to RW of 50 decibels, maybe just by filling this dry wall with the mineral wool insulation, we come to the point where the normal speech is not longer heard. And this level of insulation is usually considered as the basic for residential spaces. However, this does not mean we will not hear the neighbors if they talk a bit louder or if they decided to play some music. So we would have to go further up, let's say to 60 decibels, to make a loud speech not heard. And this wall construction, which could provide 60 decibels, could be, for example, a dry wall with a double stud construction. So you can see that there are very, very fine limits between these ratings, and all these are actually subjective. So it's not easy to make everyone happy all the time, and this is exactly the part of the story on the difference between the acoustic regulations, which maybe stand around the level of 50 decibels, and the acoustic classes, which could go even above 60 if we decide to build a project worthy of a luxurious acoustic class. So to remind ourselves, the higher the airborne sound insulation, the better it is. And the principal design strategy when we talk about the airborne sound is the careful selection of constructions which have high airborne sound insulation. With the impact sound, the situation is slightly different. Acoustic regulations will generally regulate the level of the impact sound. So just be careful, not impact sound insulation, but just impact sound. And for this impact sound, the lower the value, the better it is. To put things again into the perspective and to understand this a bit better, let's take a look at the value for impact sound for some typical floor constructions. If we have a simple concrete floor, we could expect the noise level of around 80 decibels when someone is walking on such a structure above our heads. Of course, this level will be very much different if someone walks with the soft shoes or high heels, but in this case acoustic standards go so far that they define the standard level of impact sound, and such standard level is something more closer to the high heels than to the soft shoes. So if we go to the next step, we upgrade and install the ceiling with the mineral wool below this concrete floor, we can now expect an impact sound of around 60 decibels. In case we did such an upgrade on the upper side of the floor, so we structurally separate the concrete floor and the finished floor level with a mineral wool layer, we can expect an impact sound of around 50 decibels. And if we pair these two solutions, so we provide the floating floor above the concrete slab and we provide a ceiling below the concrete slab, we can now expect an impact noise level to go even below 40 decibels. So although it's the impact sound which is generally regulated, and yes, we target the lowest possible figure for the impact sound, it's actually another quantity which material manufacturers will generally talk about and publish. And this is the delta L value, which is actually the reduction of the impact sound. And this is nothing more than the difference in impact sound between the concrete floor and the same concrete floor upgraded with a certain solution. So, for example, our floating floor has delta L value of 30 decibels. Our ceiling solution has a delta value of 20 decibels. And in this case, the higher the delta value, the better it is. So impact sound and reduction in impact sound are therefore two very similar things which usually cause a lot of confusion in the design. But what's very important to remember is the lower the impact sound, the better it is. The higher the reduction in impact sound, the better. And the principal design strategy will include the selection of separating constructions of floors and ceilings having a high reduction in impact sound. When we talk about the basic wall constructions where mineral wool is utilized, we generally have in mind these wall types. First one, the classical drywall or a gypsum wall. The next one, wall linings, so basically adding an extra layer of insulation and interior wall finish to the basic wall. And the third one, the cavity wall, where insulation layer is inserted between the two wall structures. Basic ceiling or basic floor constructions with mineral wool can again be shaped around classical concrete floors or more traditional wooden floors. An insulating layer can be added to the floor from the upper side or from below to the ceiling, as we can see in this particular image. But what is the most interesting for us are the actual acoustic effects of mineral wool. So the improvements that mineral wool brings in these constructions. Actually, one of the most often questions we face is about the actual difference in sound insulation of a certain constructions with and without the mineral wool. So let's address exactly that problem, and for the start, let's look into the effects that mineral wool has in classical drywall systems. For example, the part of this wall on the image has a mineral wool layer in the air cavity, and a small part has nothing between the steel elements. So the very legitimate question we can pose is, what is the difference in sound insulation between such two constructions? And here is the Airborne Sound insulation graph, with a reminder that the higher sound insulation value or the higher RW value means the more favorable acoustic result, or actually the better privacy between two spaces. So for this standard 100 mm dry wall, which has two standard 12.5 mm thick gypsum boards on each side of the wall and no mineral wool in the cavity, we expect an average value of RW of 37 decibels, with different performance across different frequencies. And now if we add the insulation, so if we fill the cavity of this wall with the mineral wool, here is what happens. So an increase in the sound insulation across the entire frequency range and an average 10 dB increase in the single number RW. So from RW of 37 decibels to an RW of 47 decibels. But please have in mind that this 10 dB increase is not a fixed value that is valid for every single wall structure. So the actual improvement will depend on the thickness of the partition or the number of gypsum board utilized. But generally, yes, there will always be an increase in the airborne sound insulation with adding the mineral wool. When we talk about sound insulation, the wall linings are also a very interesting subject, because this is the strategy which homeowners utilized to increase the poor sound insulation between themselves and the noisy neighbors. And what we see as a very common technique is a direct fixation of the gypsum board to the main wall, so as given in the image, without any insulating layer. So let us then compare the sound insulation for two wall upgrades. First one, done without the insulation, so with the direct adhesion of the gypsum board to the basic wall. This one achieves an RW value of 53 decibels. And the other solution, which includes mineral wool layer between the same basic wall and the gypsum board, achieve 61 decibels. So the benefit of utilizing mineral wool is quite evident in the entire frequency range. And finally, by utilizing mineral wool in the wall upgrade, brings an additional 8 dB increase in sound insulation. Now let's move from the walls to the floors. So we shall do the comparison against the basic floor structure, and in our case it's a simple 140 mm thick concrete floor. We shall compare acoustic performance, the impact sound insulation in this example, with the same floor construction, which has a few additional layers. An insulating layer of 30 mm Knauf Insulation mineral wool, and the floor finish, which can be cement screed, parquet, or just ceramic tiles. And here is how the impact sound insulation chart looks like, with the average value of impact sound for the basic concrete slab amounting to 80 dBs. Please remember that this chart displays the impact sound, so not sound insulation. Therefore, as we said, the lower the value, the better it is. And here's what happened with the impact sound when we add the floating floor with mineral wool on top of that basic concrete floor. The reduction of the impact noise is evident across the entire frequency range, and the single number rating of impact sound has been reduced from 80 to 49 decibels, so a 31 dB reduction in impact sound. The second strategy to fight the impact noise problem, which is actually a predominant strategy for renovations of apartments, when we can approach the floor only from below, so from our side of the apartment, that is the installation of a suspended ceiling. And here is the illustration of a complete sequence of such an installation. So a 45 mm Knauf Insulation mineral wool is added below the basic 140 mm concrete floor, and the ceiling is closed with a single board of a standard 12.5 mm gypsum. And here is the comparison of impact sound level for these two constructions, before and after the installation of the ceiling with the mineral wool. So there is a 23 decibel of a reduction in impact sound, from 81 decibels for a basic concrete floor down to 58 decibels to a concrete floor with the suspended ceiling. So a delta L value of 23 decibels. So all these examples that we have just seen come from the actual acoustic tests undertaken in standardized acoustic facilities, basically in the acoustic laboratories. However, there is a difference between the results obtained in these facilities and the real-life performance in buildings. And this difference in the acoustic performance between the acoustic laboratory and the construction site is often the cause of problems and disappointment with poor acoustic insulation from the homeowner side. So this is a very complex subject, but to simplify it, I like to use the analogy of fuel consumption, because fuel consumption is something much closer to our hearts and our pockets, and all of us visit petrol stations, well, much more often than acoustic laboratories. So how does the fuel consumption work? When we buy the car, the manufacturer declares an average fuel consumption, and this consumption has been very precisely measured following a very strict text methodology. So this declared fuel consumption is something which corresponds to acoustic performance, which is measured in the laboratory, with the indicators for airborne or impact sound insulation, which is on the right side of our fuel indicator. Let's say when we have a full tank. And we call these the nominal acoustic performance. On the other hand, we bought the car, now we're starting to drive the car, we immediately notice that we consume more petrol than declared by the car manufacturer. And this, in the real world, is something that we all accept as more or less normal, and we do not take car manufacturer to the court because of that. So we understand that the standard test of fuel consumption assumes constant speed, while we usually drive a bit slower or a bit faster. And that's actually what happens with the acoustic performance at the construction site. So this actual performance on the site, it's indicated with R-W and L-W on the left side of our fuel indicator. So sometimes we can build the wall perfectly, but sometimes the wall is penetrated by ducts, by pipes. Sometimes this wall carries the doors, or it just has a large TV screen built inside it. So all of these are the factors which can have endless variations that can cause difference between the nominal, the laboratory measured value of acoustic performance, and the actual value of acoustic performance which has been achieved on the construction site. And the magnitude of this degradation of acoustic performance can vary from 0 decibels, if we manage to make our installation close to perfect, or even to 20 decibels if our principal building element is severely degraded. But to illustrate that even better, let's take a look into an example of such degradation, which happens in everyday lives, and actually it's often the heart of all the complaints. So here is an office space that actually looks very nice. From architectural, from interior design point of view, we could agree it's quite a successful project. But let's now try to imagine how would this office sound. So for this particular example, I'm focusing on the sound insulation between these two offices in front of us. So a closer look at the details will let us know that the partition which separates these two offices terminates at the ceiling level. If we would open one of these ceiling tiles, there would be a large ceiling cavity expanding across the entire office space. And this ceiling cavity will most likely contain firefighting systems, air conditioning systems, electrical conduits, and other services. And from the acoustics point of view, this ceiling cavity is an opportunity, or better to call it a danger, for the phenomenon of flanking sound transmission. So flanking sound is nothing more than the sound which is transmitted around, or in our example above, the principal building element. So in our case, the partition between two offices is the principal building element, and of course we are intuitively expecting that all the sound will pass through this partition. However, in real life we end up very surprised when we figure out that we can clearly understand the colleagues on the other side of the wall because the sound is passing above the partition. So in the car owner's vocabulary, we were expecting a fuel consumption of 5 liters per 100 kilometers. And now we found out that we actually consume 15 liters per 100 kilometers. But let's switch back to the acoustics and engineering vocabulary and illustrate this example in a sectional view. So here we clearly see what's the main problem with the wall. So our carefully selected partition, which achieved RW of 60 decibel inside the acoustic laboratory, is completely out of function. Because all the sound goes above the partition, through the lightweight ceiling, or actually maybe even a perforated ceiling. And the sound reaches the other room with the actual R-W of 35 decibels. So we have a 25 decibels lower acoustic performance than we expected. A disaster. And there are no limits to the possibilities for flanking sound transmission. So flanking sound can also happen because of the penetration of surfaces. In this particular case, the architect was actually very knowledgeable, and she or he extended partition above the ceiling level to overcome that first problem. But the team which was in charge to run these services above the ceiling level was not on the same page. And of course, to make their lives easier, they have opened a considerable part of the wall to install the services. And again, the nominal sound insulating performance was degraded, and the level of privacy was not satisfactory for the end user. Sometimes such problems can occur just because of an internet cable which had to be additionally installed. So a small cable, a big hole, and a big acoustic problem. So you can imagine the disappointment of these people when they realized that their internet was now much faster, but the level of privacy was seriously degraded. And details of construction, which might seem of low importance, can also play a big part in the story of acoustic design. This example is one of the classical ones for a flanking sound transmission, which is happening around the principal building element, so around the main partition. We see a lot of these examples in the office spaces where the corridor is perceived as relatively a quiet space, because it's much easier to install the corridor wall first in its full length. This wall is done first, so with no interruptions. Then, when this wall is completed, the separating walls between the offices are built. And although these walls have been selected with insulating layer, with an extra gypsum board to provide a good level of sound insulation, in real life we will again face problem because the sound will go around the partition, not through the partition. And we will face again the degradation of the nominal acoustic performance. So in such an example, we could expect a 10 to 15 dB reduction in sound insulation from the expected laboratory value, compared to the example on the right side, where we have no degradation because the principal wall element was not interrupted. So we could go on with similar cases from the practice, but for the moment let's close this chapter and repeat the important messages. So there are two principal mechanisms of sound transfer and of sound insulation: the airborne sound and the impact sound. Mineral wool is an important part in the building elements whenever acoustic performance is important. And we should be very careful when we detail our design about the traps that flanking sound transmission can bring. And the most important of all, which we have illustrated in several examples, is that mineral wool increases the sound insulating performance of building elements. So there is an actual difference in sound insulation with solutions with and without mineral wool. And the range of Knauf Insulation products which are suitable for the indoor sound applications include Knauf Insulation rolls and boards for partitions, as well as Knauf Insulation rolls and boards for floors and ceiling. And I emphasize that our technical teams at Knauf Insulation are always here at your disposal to carefully study each particular situation separately and advise you on the most suitable product for your particular project. The second part of the webinar is in a certain way different from the previous one. That first aspect focused on the isolation from unwanted sound, but in this part we shall focus on the room acoustics, so on the quality of the sound within the space. But to define what do we actually mean by the quality of sound, first of all we need to understand what happens with the sound within a space. So what happens with the sound when someone actually says a word, or when someone actually plays a note on the violin. When a violin player plays a tone, sound travels in every possible direction. So sound goes forwards, backwards, up and down. And there is a component of this sound which comes to our ears first. And this component is called the direct sound. So this is the sound which travels the shortest possible distance from the source of the sound, from the violin in our case, to the listener. And this sound traveled without any interaction with other surfaces. In a very rapid succession after this direct sound, our ears shall receive hundreds of reflections. Some of these reflections will come from the walls, some will come from the ceiling, and from the stage. Some reflections will also come from the floor and from the seats. And the synchronization of all these components will actually define the quality of the sound that we as a listener perceive. So if our ears catch some of those reflected sounds much later than the direct sound, for example 1 second later, our brain will recognize this as the echo. But if these reflected sounds arrive very quickly after the direct sound, within a few milliseconds, our brain will have a problem to recognize what was the direct sound and what was the reflected sound. And our brain will recognize it as a very rich sound and appreciate this very strong acoustic sensation. So very generally, we can say that this permanence of sound within the space and this very fine balance between the direct sound and the reflected sound defines the quality of a sound within a space. And this permanence of sound within the space is what we call the reverberation time. And this reverberation time is measured in seconds. and it's usually considered to be one of the main parameters which defines the acoustic quality of a certain space. Now, a very good question is, what is the best? What's the optimum reverberation time for a certain space? Well, I have to disappoint you, there is no straightforward answer to this question. So there are certain types of spaces where short reverberation time is preferred. So when I say short, I mean reverberation time below 1 second. So these are typically the spaces such as offices, meeting rooms or classrooms, where it is the spoken content which is predominant. So our main intention in such a space is to make the spoken content understandable. On the other hand, the spaces where music is of an importance, we benefit from a longer reverberation time, usually exceeding 1 second. So opera lovers, for example, will appreciate reverberation time of 1.5 seconds, and it is said that Mozart might sound the best with a reverberation time of 2 seconds or more. So you can see there is a very fine and fragile limit between these values, and actually that's the beauty of acoustics, because there is no strict rule what is good and what is bad. But our general idea and our target is to make the speech intelligible and to make the music strong and clear. And we use reverberation time as the convenient way to express and quantify that. Reverberation time, it's directly related to the volume of the space, therefore to the size of the space and the sound absorption of all the room surfaces. Again, this is something very intuitive, so you can imagine that the larger space will sound more reverberant, and space with more sound absorption, so with more soft elements, will sound less reverberant. And it can be easy to understand how the materials such as carpets or curtains help in controlling and in balancing reverberation time. But what is the benefit and what is the acoustic effect of mineral wool when we talk about the room acoustics? So one way of utilizing the mineral wool is to pair it with other materials which are often used in interiors, such as the ceilings. So let us take a look how mineral wool improves the acoustic performance of a ceiling, in this case a perforated ceiling. This again is the sound absorption chart for a classical perforated ceiling tile system. So this system just by itself has already a decent sound absorbing property. So if we put an average alpha value on this chart, we could say it's roughly around 0.55. In this case, we can say that because of the perforations, some of the sound is trapped in the ceiling cavity, and actually that's why the perforated ceiling provides some sound absorption by itself, unlike the standard gypsum ceiling, which would have a negligible sound absorption. So a standard gypsum ceiling would have most likely an alpha value close to 0. After adding the mineral wool insulation on top of the ceiling, here is what happens with the sound absorption. We have an increase across all the frequencies, and the average increase from 0.55 to 0.9 of the sound absorption coefficient. So these things look very straightforward, but they are often confusing, and it's not so easy to talk in the terms of alpha coefficients, of reverberation times, because even for professionals, it's not easy to imagine how would a certain space sound, even if we know the size of this space, or even if we know the characteristics of every single material we plan to utilize in this space. However, modern technology managed to overcome this communication problem. So today it's possible to simulate the acoustic conditions of any room just by having the inputs of its size and the materials used. So let's take this meeting room as a simple example. On the first look, we can notice the extensive use of glass and gypsum, and we could make an educated guess to expect around 1.1 seconds of reverberation time in such a space. But still, it's very hard to imagine how would this meeting room actually sound. So for the moment, let's technology do the work for us, and let us listen on how would a simple sentence spoken in this room sound. Luckily, we can see what has been said, because it's quite difficult to understand it. And this is something that all of us would call echoic space, and actually acoustically very poor space. Although from design point of view, from the interior design, it looks quite good. As we could not have a meeting in such a space, okay, let's move to another meeting room, and this one still looks good and modern, but unlike the first one, it incorporates some mineral wool which is hidden behind these wooden slats on the side walls, and it has some mineral wool above the micro-perforated wooden ceiling panels. So for this space, with some acoustic treatment, we would expect a reverberation time of 0.6 seconds. But again, how would this meeting room actually sound? So now let's listen again to that same sentence.
Symphony Hall, still considered one of the best halls for music in the world.
Well, that sounds much better now. But to use the power of mineral wool and what sound absorption can do for the acoustic quality of a space, you don't need to rely only on perforations. So there are solutions from Knauf and its partners where sound absorption can be achieved with a solid look without any perforations at all. Actually, there are no limits to your design ideas, so even the wood wool products provide exceptional sound absorption and they look great, either used on the ceilings or on the walls. So the only limit to the acoustic design is your imagination. As we have mentioned the wood wool products, apart from using them in the interiors because they look so good, one of their typical applications is to the ceiling of underground parkings. And the reason for this particular application is actually twofold. First, to increase the sound insulation to the space located above the parking. And second, which is a very interesting aspect of room acoustics, but unfortunately very rarely discussed and often neglected, is to increase the speech intelligibility and enable the voice communication capability. And this is very important if we consider evacuation and emergency messages which are delivered through the public address system. This is a very important safety aspect, and it's tightly related to the reverberation time of large public spaces. And this is actually quite often a problem in spaces such as underground parkings, train stations, airports, or shopping malls. Very often at the airports, we are not able to understand messages which are related to departures or arrivals because of the bad acoustics. But more important would be the emergency evacuation messages whose poor intelligibility can even lead to misfortunate events. And here is a sound absorption chart for a wood wool board Podán by Knauf Insulation compared to the aerated concrete of same thickness. So there is quite a difference between the two in the entire frequency range, and the difference of 0.6 in the average alpha value. So from 0.35 for the aerated concrete to 0.95 for Podán, for a wood wool. So similar to wood wool, aerated concrete is also used for the ceilings of parkings. And the aerated concrete would fulfill that first part of the acoustic task to increase the sound insulation to the space above the parking. However, its low sound absorptive capacity would make the parking a very echoic space, and you would struggle to understand what has been said through the public address system. So for such large spaces, more sound absorption will lead to a lower reverberation time, and this lower reverberation time will lead to a higher speech intelligibility. And here are the important messages related to room acoustics. We've mentioned the importance of the fine balance between the direct and the reflected sound. We have discussed the need to optimize the reverberation time, keeping it a bit shorter for the spoken content and a bit longer for the music. We have discussed some strategies on how to control the reverberation time and presented unlimited design options. And finally, we've mentioned the importance of speech intelligibility in large public spaces and the advantages that wood wool solutions can offer in such applications. So what to capture is that mineral wool adds additional sound absorption to the space and aids in reducing the reverberation time. There are numerous products in the range of Knauf Insulation which can be utilized for the purpose of reverberation time control, such as the wood wool boards suitable for exposed ceilings, especially underground parkings, or the classical insulation rolls and boards used for ceilings and walls. But let's now move from the interior of the building to the building envelope. And let's talk about the third aspect of the acoustic design, the insulation from outdoor noise. Some of us are very lucky to live in isolated and remote individual houses. And for such objects, the outdoor noise is actually not even an issue. But apart from those few very lucky individuals, the world is becoming more and more densely populated. So there is more and more people on the planet, and more people are moving to the cities. So we could generally say that our future has a more urban than a rural perspective. And this is how this urban perspective looks like in Hong Kong. This is maybe a bit of an over-exaggerated example, but a good example to imagine the levels of noise which might be present in such a dense urban environment. And typical sources of outdoor noise are traffic, which can include road noise, trains or aircrafts, then the various building services, which are often installed on the roofs of neighboring buildings. Outdoor noise can also be emitted from industrial sites and production facilities, which are quite often causing the problems to residential areas, or even the entertainment noise, such as the noise related to sports events, stadium rock concerts, various outdoor events, or just simple nightclubs. And to give you an idea about the magnitude of noise in a typical urban environment, which usually consists of a mix of traffic sounds, human conversation, and some building services noise, that typically amounts to 65 to 70 decibels. On the opposite end of this scale is something which we can consider as a comfortable interior level. And this ranges between 30 and 40 decibels. Let's say that 30 decibels would be quite a good level for a bedroom, and 40 decibels would be quite a comfortable level for a working space or an office. And our first weapon as designers, our design strategy against the outdoor noise is so-called shielding of noise-sensitive areas. So noise-sensitive areas would be rooms such as bedrooms, hotel rooms, maybe libraries, and similar spaces where rest or concentration is important. So shielding would then imply a careful arrangement of these areas, so not to locate them close to main roads or to neighbors' air conditioning units, or basically away from any similar noisy hotspot which might be problematic for our facade. And this is something very intuitive and very effective as a design trick, but we don't always have the commodity to locate all the noise-sensitive areas where we would want to. Because sometimes our balcony and bedroom inevitably ends up facing the main street, the train station, or just some simple noisy object like maybe a car wash station in front of our home. And in those cases, we do have to apply some acoustic strategies. Generally, we differentiate two acoustic strategies. First one is the noise reduction at the source of noise, and the second one, which is interesting for us when we discuss the building facade, is the noise reduction at the building envelope and the design of suitable facade elements. Here's a quick and simple illustration of the standard facade elements. So our first line of defense against the noise from outdoors is pitched roof, a flat roof, contact facade or the attic system, and ventilated facade. So what are the effects that mineral wool has in a facade system? So let us look into the external wall, which is usually our first line of defense. For example, we have a concrete wall as our basic wall construction. The sound insulation, the RW of such a wall, amounts to 59 decibels. And let's not forget that the higher the RW is the better when we are discussing the matters of airborne sound insulation. And noise from outdoors falls into the category of airborne sound insulation. So this is how the sound insulation graph of our base wall, the external concrete wall, looks like, with the RW value of 59 decibels. If we add the facade system, the attic system with mineral wool to the external wall, we will provide an increase in airborne sound insulation, so the increase in RW value of 11 decibels, from 59 to 70. To make things a bit more interesting, let's now add to the same graph the attic system of a same insulation added to the same base wall, but this time based on EPS insulation, on the polystyrene. So we can immediately notice something very strange. So sound insulation of the basic wall is now reduced in the lower frequency range, and this eventually causes the single number rating, the RW, to fall by 3 dBs, so from 56 to 59. And this reduction in the lower frequency matches the frequency of that hum that the traffic noise usually produces. So eventually, instead of increasing the sound insulation of the external wall, which would be intuitive because we are adding extra layers of insulation, we actually reduce the sound insulation of the external wall, and we actually reduce it exactly in that frequency where traffic noise is usually the most predominant and most annoying. So this particular effect of reducing acoustic performance of the basic wall is directly related to the rigidity of the insulating layer. So this example outlines the difference between insulation such as mineral wool, which has more open pore structure, and in this example the polystyrene, which is generally more rigid and has a more closed pore structure. But now we could imagine a large variety of materials which would fit between these two curves. So some materials could increase and the other materials could decrease the sound insulation of the basic wall. So again, we're coming to that story that there is no the best material for every single purpose. Rather, there are materials which are the most suitable for a certain application. Here is another example of effects of mineral wool in facades. And this time we can illustrate it on a wooden structure, which is becoming very attractive these days because of its appearance, the green building story, and the energy efficiency. And in this case, our basic wall is a cross-laminated solid wood structure with an RW value of 34 decibels. And if we plot this wall on the sound insulation chart, here is how the curve of 34 decibels looks like. We can again see that addition of the insulating layer causes the sound insulation to rise, again across the entire frequency range, with an overall increase of 28 decibels. So from an RW value of 34 for the basic wall to an RW value of 62 decibels to an isolated basic wall. And this is actually how this particular construction looks like. So on the inner side, to the interior of the building, we have a 40 mm insulation board with 2 standard gypsum boards, and on the outer side of the basic wooden element is a 100 mm thick insulation board with a facade coating. So we're talking about a complete facade system. For the very end of this fundamental aspect of acoustic design, which is outdoor noise, one particular aspect which does not often cross our minds when we start with the design process, the rain noise. And the rain noise is the most prominent on metal deck roofs. So actually, the aspect of rain noise is even regulated in some countries, but regardless of that, rain noise can be quite annoying if you happen to live in the attic, just below the metal deck roof. And these kind of constructions are these days very popular for schools and even multi-purpose halls. So now you can imagine it would not be easy to listen to the lecture in a classroom or to a classical music concert in a multi-purpose hall if it happens to be on a very rainy day. So rain noise is maybe not on our minds as a designers quite often, but we still take it quite seriously, and actually we do perform acoustic tests to measure the impact that rain noise has. And in one of the studies which was undertaken recently, rain noise on 2 roofs was compared. And as we're talking about the noise level, the lower value is more favorable. So a typical metal construction, such as this one, insulated with Knauf Insulation mineral wool, yielded the result of 35 decibels once it was exposed to rain. And the rain noise for the similar roof construction but using the foam as the insulating layer produced 60 decibels in the space below the roof. So 25 decibels more noise compared to the roof with a mineral wool solution. And again, it's the porous structure of the mineral wool, the principal reason for the improved acoustic performance, even in this very particular application. And in the end, to summarize what we've learned about the insulation from outdoor noise. So typical outdoor noise levels are in the range of 65 to 70 decibels in standard urban areas. Comfortable interior noise levels range somewhere between 30 and 40 decibels. And the building envelope is that element which actually presents the barrier between outdoor noise level and indoor level of acoustic comfort. With several real-life examples and actual constructions, we have also outlined that the correct selection of insulating layer increases sound insulation of facade system or even reduces the level of rain noise. But on the other hand, we also did see that misfortunate selection of insulating material can sometimes lead to a reduction of sound insulation. At Knauf Insulation, we provide a wide range of products which are suitable for all the facade elements. Such are the insulating boards for contact facades, rolls for pitched roofs with our ECOS technology using the bio-based binder, or boards for flat roofs. And the most important is that we do have the knowledge and we do have the experience to advise you on the optimum solution for each particular facade type, depending on the requirements and your ideas behind every individual project. So part 4, the fourth fundamental aspect of the acoustic design, noise of building services. So there are numerous types of building services, and eventually in real life we can even experience noise with the simple buzz of a light bulb. But generally, there are certain building services which are considered as the main sources of noise and the main sources of potential problems. These are typically the elevators, the plumbing systems, air conditioning units, or complete equipment rooms, which can house anything from central climatization systems to swimming pool pumps. I'll start with the elevator's noise, as I've personally lived in a lot of buildings and I've spent nights in many hotels where I could hear every single stop and start of the elevator. So the principal design strategy when designing the elevators is to separate the elevator, so the elevator shaft wall, from the noise sensitive area. Again, if we are limited with options and we can't escape from these situations, the correct acoustic strategy would be to structurally disconnect the common wall between the room and the elevator shaft, because that's the wall which usually has a very large surface and transmits the sound from the elevator's movement to our ears. And a very similar problem happens as well in the case of equipment rooms which are located next to the residential areas. And here is a layout for one typical residential building. So we can notice the central core, which houses 4 elevators and the staircase, with residential spaces located around the core. So these upper 3 elevators are very favorably located. They are next to the corridor, they are next on the utility space to the right, but this 4th elevator looks like a problem because it shares a wall with the living room and it shares the wall with the bedroom of these 2 neighboring apartments. So this is something which can pass relatively unnoticed during the design stage, but in the end, if this building opens, the tenants would most likely complain about the noise coming from this elevator. So how to solve such a problem? Generally, we classify such a challenge into the category of wall linings or wall upgrades, but with the very important detail of structural disconnection between this wall lining and the elevator shaft. Such disconnection can be achieved with special brackets or just by connecting support steel structure to the floor and the ceiling alone, with the mandatory insulation layer of mineral wool and additional wall boards. So this upgrade will certainly reduce the problem, but there is still a path for the noise transfer with the connection of the elevator to the floor slabs. And these particular details are very difficult to solve during the renovation. Although, yes, we could introduce a secondary ceiling, a floating floor, and achieve complete and much better insulation. But better solutions can be done in the early design stages. And that's a very important message, that acoustic solutions are much more easier to implement and much cheaper if they are considered in the early design stages. That's why for every architect, it's important to have a strong partner, a strong technical team with a wide range of acoustic solutions from day one of your design process. Another usual problem with building systems are the plumbing noise issues. And this noise is usually related to the water supply and drainage systems. So the most simple case would involve us hearing the neighbors when they take the shower or flush the toilet. So in this illustration, we can realize the benefit of a structural decoupling with mineral wool, which is actually preventing the water flow to be transmitted to the pipe and from the pipe to the entire building structure, in case we had a rigid fixation, if this mineral wool strip was missing. So plumbing sound, in that case, could easily travel up and down the building, even through several floors. So to summarize this part of the noise of building services, we have highlighted the importance of a structural disconnection and mineral wool infills. But again, owing to its porous structure, mineral wool is highly effective in reducing noise levels of building services, as well as aids in the structural disconnection of building elements. And Knauf Insulation products suitable for these applications are Thermatech and PowerTech rolls and boards, which are great for applications where the space constraint is an issue. And they are also suitable for application around the pipework and ventilation channels, as well as our traditional Knauf Insulation rolls and boards for partitions, so basically for wall linings and wall upgrades. After protecting ourselves from the outdoor noise, now we shall take a look on how to protect others from the noise that we and our project might be creating and introducing into the environment. For a good illustration, let's again use an example of a densely built area. And if you look very closely at these facades, you will notice that there is at least one air conditioning unit for each apartment. And in this case, it's these window types air conditioning units, which are maybe amongst the, well, noisiest units out there, but still they're used across the world. So you can imagine how horrible this entire space, this entire internal courtyard sounds when all of these air conditioning units are working at the same time. So typical sources of noise which cause impact to the environment are air conditioning units and various items of mechanical equipment. This can be from pumps to heat exchangers, exhaust fans, and usually these are located in the equipment rooms, which will have some openings on the facade, typically for air intake, or generally on the roofs of our objects. And it's not so grateful to give an estimate of typical noise levels which is produced by these sources, because they're all very much different between themselves. But often, especially in the case of mechanical equipment, more important than this average noise level is even tonal noise. So basically a certain tonal component which drives everyone crazy, a certain frequency, certain buzz, just a certain pitch of the sound which is particular for every single item of equipment. And how do we fight such problems? Well, in the previous chapter we have focused on noise reduction at the level of the building envelope. But now we resort to the strategy of reducing the noise at the source of the problem itself. So from a design perspective, that would mean doing our best, usually together in coordination with mechanical engineers, to locate the items of equipment which shall be noisy away from noise-sensitive area. So basically away from our own bedroom and away from the neighbors. Good locations are usually the nearby main roads or open roads. However, when we can't avoid certain impact to the environment, we do have to think about certain acoustic solution. This is a good illustration of what reducing the noise at the source actually means. So our insulation is very often used to fabricate casings and enclosures for the equipment. It's often used as the acoustic infill for sound attenuators, or it's used inside the acoustic louvers, which enable the circulation of air but still reduce the noise level which we emit into the environment. And all this noise reduction happens exactly because of the high sound absorption that mineral wool provides. Because as we force the air and the sound to go through a certain space, which is padded, which is lined with the mineral wool, sound tends to get reduced. Here is one such solution implemented at our own factory in Slovenia, where relatively a simple elbow padded with mineral wool insulation prevented the noise to be transmitted from the fan, which is located behind this elbow, to the neighbors. So our insulation can be easily shaped to fit any custom solution, and that's why it is so useful for such tailored applications. And on this particular example, you can notice that the finishing of the insulating layer is black. That's because of the facing, which is applied to the insulation. And this particular facing has been applied to prevent mitigations of fibers due to the airflow. So it's often the case that apart from noise pollution, we need to consider health or hygienic requirements too. So what's important to capture from this story about the noise impact to the environment is that the most effective strategy of mitigating the noise is if we reduce it at the source itself. And for these particular purposes, typical acoustic measures include acoustic barriers, acoustic enclosures, the blankets, or some more complicated devices like sound attenuators or acoustic louvers. And from the design and coordination point of view, locating the noisy equipment as far as possible from noise-sensitive areas is always a good choice. And in all these applications, it's again mineral wool that aids in reducing the noise levels emitted into the environment. So for this particular application, we at Knauf Insulation have a dedicated range of products for technical solutions. So these are our Thermotech and PowerTech insulations, which are generally very easy to shape. So their installation is very easy. And usually these applications happen to be in very constrained spaces. So it's also possible to fabricate all these products with a variety of facings which are suitable for every particular application. And this brings us to the end of our webinar. I hope that you enjoyed it and you've gained a lot of new and useful information about the acoustics. I'm also hopeful that you will revisit the webinar and use it in your daily work when you face an acoustic challenge. We at Knauf Insulation are always here at your disposal and ready to help you and assist with any acoustic problems or challenges you might face in the future. Thank you.